Hello students. Today we are moving to our second module. So this is the first part of our second module. So with the previous 6 to 7 sessions, we have completed the first module. I think we should do some problem. I will based on first module, I will upload some sample solved problems as PDFs or notes and your modules. Okay, so now we will move to the second module in or RAC, refrigeration air conditioning system, and this module deals with a very important concept called vapor compression refrigeration system, or called as VCRS. So VCRS is nothing but vapor compression refrigeration system. So students, in the previous module, we have learned a concept, a working cycle called Bell-Coleman cycle, right? Bell-Coleman cycle. So what was Bell-Coleman cycle, or simply a reversed Joule cycle, or a reversed Joule cycle? Actually, that was a cycle based on air as the working fluid. There, air was working fluid. Air was working fluid or refrigerant. It is also known as a refrigerant because in refrigeration cycle, the working fluids are known as refrigerants. Refrigerant. Okay. So in Bell-Coleman cycle or reversed Joule cycle, the refrigerant was air. That means the working fluid was in a gaseous state. So there was no change of phase for the air during the cycle. During the entire cycle, air remains as air itself, that is in gaseous state itself. There was no change in phase taking place in the case of air. The heat transfer, the heat was transferred from, it was extracted from the refrigerating space, and it was compressed and then moved to condenser where it rejects heat to its surrounding and then expanded to the pressure of lower pressure and then came back to the refrigerator again. So there actually heat transfer was taking place, but that heat transfer, the heat was extracted and rejected in the term uh, in its sensible form only, right? There it was in sensible heating or sensible cooling was taking place. Sensible heating or sensible cooling is that type of heating or cooling where only change in temperature takes place, right? Sensible heating only, sensible heating or cooling of air. That means only change in temperature is taking place, either increasing or decreasing, depending upon whether it is in condenser or evaporator. But no change in phase, no change in phase. So the air remains as remains in its gaseous form itself. Okay, so that was the things happening in your Bell-Coleman or reverse Joule cycle, right? So here, when we come to vapor compression system, so in VCRs, so what do you mean by VCRs? So VCRs is an improved type of air refrigeration system in which a suitable working substance is used. Okay, in which a suitable working substance is used, and the refrigerant undergoes condensation and evaporation. Refrigerant or working fluid undergoes evaporation and condensation. That means, what does that mean? It means that there is a considerable or considerable phase change taking place, right? Phase change is taking place. In evaporation and condensation means, evaporation means the change from liquid state to vapor state. Condensation means getting back the change from vapor state to liquid phase. So phase change. So here phase change is taking place. That is very important. Okay, very important. Phase change is taking place. So during evaporation, what happens? it absorbs heat from the cold body or the body to be refrigerated. This heat is used as its latent heat for converting it from the liquid to vapor, correct? So in condenser, it rejects heat to the external body or atmosphere by rejecting its the latent heat, right? And thus creating a cooling effect in the working fluid. Understand? I will explain more elaborately in coming sessions. Now you understand the basics that normally in a refrigeration system we have some evaporator or heat exchanger here from where heat is extracted from space to be cooled. Space to be cooled, heat is extracted from space to be cooled, and this fluid and the working fluid extract heat from that heat exchanger and move to compressor where temperature and pressure increases. Then it move to another heat exchanger where it rejects heat to atmosphere or any other sink, then comes back through an expansion valve, right, expansion device, and it is ready to absorb heat again from the space to be cooled. So this is what happening actually in VCRs. This thing will be an evaporator. The heat exchanger near the heat exchanger present in the space to be cooled is an evaporator, and the heat exchanger which rejects heat to atmosphere will be condenser. Okay, so in evaporator, what is happening to the evaporator? What is happening to the refrigerant? The refrigerant absorb heat from the space to be cooled, and it gets evaporated, and the heat absorbed will be latent heat, and it is used as latent heat for converting it from the liquid to vapor. So at evaporator, the refrigerant will be initially in a liquid form. It absorbs heat and it becomes vapor, and this vapor move to compressor. Compressor will increase its pressure and temperature above the atmospheric condition, and from this condenser it rejects heat to atmosphere by it will return back to actually here the refrigerant is in vapor form. After rejecting heat to the atmosphere, the refrigerant in its vapor form will come back to its liquid form, and liquid form partially it will become liquid, and after passing through expansion it will be completely converted into liquid form, and it again reaches evaporator for further for the continuation of cycle. So the cycle repeats. So this is what is happening in VCR system. I will explain these things in a better way in coming session after understanding the basics of this cycle. Okay, don't worry. So for the time being you try to understand that here phase change is happening for the what refrigerant for that is evaporation is taking place in evaporator and condensation is taking place in condenser. Okay, so that is the basics of vapor cycle. Actually VCRS is a vapor cycle VCRs, and Bell-Coleman cycle is a gaseous cycle. Bell-Coleman cycle is a gaseous cycle, gas cycle. Okay, so that is a basic difference. So in gas cycle there is no phase change, in vapor cycle there is a phase change. Now we will compare comparison between gas cycle and vapor cycle. Comparison. Vapor cycle and gas cycle. So in a gas cycle, the working fluid is gas, does not undergo phase change, right? I will gas cycle vapor cycle. Okay, here no phase change. Here yes, phase change is there. Here phase change is there. Next, in gas cycle, heat rejection and heat absorption take place as the gas undergoes sensible cooling and heating. So in heat exchanges, sensible heating and cooling takes place, right? And here in heat exchanges mean here it is evaporator and condenser. So here what happens? Latent heat of latent heat and cooling, latent heating and cooling. So in evaporator, it absorbs latent heat and convert it in convert from liquid state to vapor state. In condenser, it rejects latent heat of cooling and convert back from vapor state to liquid state. That is latent heat of vaporization. Here, latent heat of condensation. Latent heat of vaporization and latent heat of condensation. So if the refrigerant is a pure substance, then its temperature remains constant during its phase change process, right? So you know that those basics because you have already studied in thermodynamics, right? So if the in the case of phase change, the temperature remains constant here. Here temperature remains constant. Gas cycle. Yes, vapor. So here during phase change, T equal to constant. Here T varies, right? Temperature varies, right? So during phase change in case of vapor cycle, the temperature remains constant. Hence, the required mass flow rates for a given refrigeration capacity will be much smaller. Here, the mass flow rate required of the mass flow rate of refrigerant required will be small. Here it is. Here m dot is high, mass flow rate is high, and here because compared to the sensible heat, latent heat is very high. For unit mass, the latent heat of vaporization, latent heat of condensation are a large value. So you know, students, total heat will be m dot into L. If L is very high, m dot required will be low for the same amount of Q, right? If Q remains constant, if L dot the latent heat of vaporization is very high, means m dot required is very low. So we require only smaller mass flow rate in case of latent heat. But in case of sensible heat, mcp delta t, right? M dot cp delta t. Here cp will be, if cp is constant, or if we require large amount of heat to be transferred, either we have to attain a large either we have to get a large temperature reference, or either we have to use cp with a gas with a very high cp. But these things are impossible, so we have to naturally increase the mass flow rate for getting a particular value of Q. But if you compare this value with m dot L, this will be very higher. So that is why we are using VCRS. Okay, VCRS system. So vapor cycles, and there are different types of vapor cycle. Vapor combustion systems are there, vapor absorption systems are there, that you will study later. Now students, I will try to show you a simple vapor combustion system, or simple simple VCRS in our TS diagram. Okay, temperature entropy diagram. I will show you. Students, here actually it consists of four different process from one to two actually. So before that, since we are dealing with a vapor compression system, right? We have to use the phase change diagram in case phase change is happening. So we have to draw this dome. So students, this dome for the particular for that particular what refrigerant. This is for a particular refrigerant. So here this dome. This is a vapor dome. Actually, here vapor exists. The refrigerant exists as liquid. Here inside the dome, refrigerant exists as liquid plus vapor. Outside the dome, here it is vapor itself. Okay, so this dome you learned in your thermodynamics class or thermal engineering class and all steam engineering subjects, right? Steam cycles you have learned. So I think you are well aware of these concepts, right? So students, you also know how to draw constant pressure lines in TS diagram. Constant pressure lines are like this. So inside the dome, constant pressure lines are horizontal. Outside the dome, it varies like this. Okay. So this is another pressure. So this is P1, this is P2, and P1 will be greater than P2. So higher pressures will be drawn at a higher level. So that is the concept. So okay, so you know the basics, right? Now I will draw the process happening in what a simple refrigeration system. Okay, so the process is like this. From one to two, constant entropy compression. Okay, 2 to some 2 dash. This is a constant pressure. So this is 2 dash. Okay, 2 dash to 3, constant pressure heat rejection, and 3 dash to 4 is a constant enthalpy process, and 4 to 1. So this is the cycle 1 to 2 to 3 to 4 to 1. So this is our cycle. Okay, so students, what is happening here? So first process is 1 to 1, 1 to 2. Here it is S is constant, means entropy constant, means isentropic process. Since temperature is increasing from 1 to 2 and pressure is also increasing. So when you go vertically upward, pressure increases. So this process is isentropic compression. Okay, isentropic compression. So 1 to 2 is isentropic compression. So students, you should note that what is the state of refrigerant at 1? The state of refrigerant at 1 is, it means here, since it is it is present on the that dome, that curve, right? So this is vapor curve, gaseous curve. So this is liquid. Here in this part will be liquid, okay, and this part will be vapor, right? So students, at this portion means it is vapor. So at the inlet of compressor, the state of at the inlet of compressor, state of refrigerant is what? Dry vapor, right? Vapor is completely dry, saturated vapor. It is also known as saturated vapor. So this saturated vapor undergoes what? Isentropic compression to 2. Okay, isentropy compression to 2. So entropy remains constant from 1 to 2. isentropic compression. And next, what is happening? 2 to 2 dash to 3. Okay, 2 to 2. What is the state of vapor at 2? State of vapor at 2 is nothing but superheated. So at one saturated vapor. Condition is saturated vapor, okay, or dry vapor. At 2 superheated vapor. After compression, it will become superheated vapor. So what is the process taking place from 2 to 3? 2 to 3 is nothing but constant pressure heat rejection. Constant pressure heat rejection, or what is happening, constant at constant pressure heat is rejected. So here it is vapor, right? After constant pressure heat rejection, it here it is L plus V, here it become at 3. So students, I will write at two dash, it becomes when constant pressure, when heat is rejected at constant pressure at 2 dash, it will become what what is the state of reference 2 dash? Vapor or saturated vapor, saturated vapor. And at 3 it becomes saturated liquid. So saturated liquid. So from 2 to 3 it has undergone a condensation process. So 2 to 3 is also known as condensation is taking place. So the refrigerant gets a phase of change from superheated vapor form to saturated liquid form, right? So here it is nothing but, this is nothing but condensation. Okay, now from 3 position 3 it is vapor, sorry, liquid, right? This is liquid. Okay, and this process is constant pressure. Okay, and 3 to 4 it is H constant, enthalpy, isenthalpic process. Okay, H is constant. So H constant means it should be a curvy, it should be little bit curvy. We'll draw once more. So it should be a curvy. In TS diagram, H constant lines are somewhat curvy. So this is, since this is expansion, its arrow is downwards. So 3 to 4 is an isenthalpic process of expansion. Isenthalpic expansion process. So at 4, what is the state? It is a mixed vapor. Okay, or a wet condition. This is not dry, wet vapor, not saturated, or not saturated vapor, not saturated liquid. It is a mixture of liquid and vapor. Since it is present inside the dome, it is a mixture. So when it reaches the, so what is the process? 3 to 4 is nothing but isenthalpic expansion. Isenthalpic expansion means pressure is decreasing, temperature is also decreasing, and the vapor is the saturated liquid is what happened to that liquid? It just get converted into liquid vapor mixture, a wet mixture, right? Wet mixture. And now 4 to 1, what happens? 4 to 1, 4 to 1 is a process of constant, since this is horizontal, it means a constant pressure process. So constant pressure heat addition, right? Constant pressure heat addition. So what this heat is adding, in what form heat is getting added? Latent heat of evaporation. So 4 to 1 is evaporation. Evaporation. Heat is added at a constant pressure. Constant pressure. And the refrigerant becomes a saturated become after absorbing heat in the form of latent heat of vaporization, it gets evaporated and it becomes what saturated. It becomes a saturated vapor form. From where this heat is added, the heat is added from the space to be cool. So students, here you have to note that what actually is taking place here. Here this is evaporation. This process is taking place in evaporator. So heat is added from the space to be cool. From the space to be cool, heat is extracted by the evaporator. Okay, heat is added and it becomes saturated vapor. This saturated vapor undergoes isentropic compression. So this is evaporator and this is compressor. So this saturated vapor undergoes isentropic compression in the compressor, and its temperature and pressure increases after when it reaches higher pressure and higher temperature. Here what happens? From superheat it becomes superheated vapor. This superheated vapor is converted back to saturated liquid. So what happens? Condensation takes place. How condensation takes place? By rejecting latent heat of condensation. So this heat is rejected to where? Atmosphere. Atmosphere. The heat is rejected to atmosphere. Okay. So Q is rejected to atmosphere. So this process is taking place in condenser. Condenser. So from condenser, the what is happening? The temperature gets lower, but the pressure remains constant. Temperature gets lower, pressure remains constant. So in order to decrease the pressure to our lower pressure available in evaporator, it undergoes an expansion process. Expansion takes place isenthalpic way. So enthalpy remains constant and pressure decreases to the evaporator pressure, and it reaches evaporator as a mixture of liquid and vapor, and this liquid and vapor enters the evaporator and absorbs heat again, and the cycle continues. So this is the working of a vapor compression refrigeration cycle. Okay, vapor compression refrigeration cycle. So students, this figure shows the mechanism of simple vapor refrigeration system, and the various systems. You can see the various components of a vapor compression system, a simple vapor refrigeration system here. So students, you can see first one compressor here, and next after compressor it reaches. So this is condenser. Okay, a receiver is there. I will tell you the function of receiver. Don't worry. And next expansion after receiver there is an expansion valve, and this is the evaporator. So these two are heat exchangers. Here condensation takes place. Here evaporation takes place. This is compressor and this is expansion valve, and an extra term, component called receiver is also there. Okay, so I will tell you the function here. So from a figure, I will show you the figure. So basically, this is our figure. So here 1 to 2 is the process from compressor. So 1 is the state of refrigerant inlet of. So at the inlet, the state of refrigerant is 1. So here you can see 1. at inlet of compressor it will be 1, and outlet is 2. Okay, so students, what is happening in compressor? The low pressure and low temperature, low pressure and a bit higher temperature vapor refrigerant from evaporator is sucked or drawn into the compressor through the inlet or suction valve, right? So the low pressure, low temperature, uh, low temperature vapor refrigerant in saturated vapor form, it is getting sucked through the suction valve of A, right? So you can see this A is a suction valve. So it is getting sucked into the compressor, and after compression it is then compressed to a higher pressure and higher temperature vapor refrigerant. So at 2, what will be the state of? So at 2 it is superheated form. After compression it will become superheated form. So students, why are you applying pressure and temperature to this refrigerant? What is the reason? So you are applying, you are compressing it, right? This higher pressure, the refrigerant becomes the saturated vapor becomes a superheated vapor. Superheated vapor means it has got higher pressure and higher temperature. So why are you doing that? So applying pressure means applying pressure by compressing pressure increases, temperature increases. Okay, so pressure increases means you are setting a pressure differential there. So by setting a pressure differential using compressor, pressure difference, okay, a pressure difference is required. You will be able to move the refrigerants around that different through the different components, right? Only if there is a pressure difference, any liquid or any gas or any vapor moves through the different parts. If there is no pressure difference, means the liquid will be in stagnant state, or it won't move, right? So pressure difference is a must. It is the driving potential for the movement of the cycle. So that is why we require a pressure compressor there. So when the pressure is increased, the liquid or the refrigerant will move towards the lower pressure side. Then only a movement is set, right? Okay, that is the reason for using a compressor. So you have understood. So students, after compression, what is happening? Some 2 to 3. What is 2 to 3? 2 to 3 is up to here. Okay. So 2 to 3 it is movement through condenser. So students, so this it is known as high pressure line. So here you can see high pressure side. So the compressor, from compressor, the line moving from compressor to condenser is known as high pressure side, because it is at a high, the refrigerant is at high pressure. So it is actually in high vapor form, high pressure vapor, and this vapor is passed through the what, condenser. So condenser, what happens? It rejects heat to what, atmosphere. So students, in order to reject heat, so suppose atmosphere, the temperature of atmosphere is Ta, temperature of refrigerant here is Tr. So in order to reject heat from condenser to atmosphere, if there is a heat rejection, heat transfer from refrigerant to atmosphere had to take place, what will be the condition? Tr should be greater than Ta, then only heat get transferred. Heat get transferred from higher temperature to lower temperature only. So we have to achieve a temperature higher than ambient temperature, right? We have to achieve a temperature higher than ambient temperature. That is one another function of the compressor, right? So here by compressing we are increasing temperature, right? Why we are increasing temperature? Because we have to get a higher temperature than the temperature of the atmosphere, so that we can reject heat to the atmosphere. Understand? Have you understood? Yes. So that is why we are using compressor to increase pressure and temperature. So students, you have understood what is happening in condenser. So here pressure remains constant. So here in this condenser, pressure remains constant. Temperature varies by temperature is getting varied as heat is getting rejected to atmosphere. So students, you can see here, you can see that naturally it is getting into liquid form. So here blue, you can see a blue color. So it becomes high pressure liquid vapor mixture, right? So that is what here. This is a liquid vapor mixture. Liquid vapor mixture. So since it is inside the dome, this is a liquid vapor mixture. So after getting converted into a liquid vapor mixture, uh, you can see that here a component called receiver is there, right? So receiver, what is the function of receiver? The condensed liquid refrigerant from the condenser is stored in a vessel known as receiver, from where it is supplied to the evaporator through the expansion valve. So this is used for storing the condensed liquid refrigerant for just some time. So from this receiver only it moves to evaporator through the expansion valve. So it is just for the storing purpose. Okay, no much significance in this cycle. You don't have to mark receiver in your TS diagram and all. Okay, so that is a receiver. So now high pressure, but pressure here is still high. So still pressure is high, right? So here it is constant pressure process. Now pressure is not still lower. So pressure is still high. Now this high pressure, low temperature, pressure liquid vapor mixture. High pressure, low temperature liquid vapor mixture is now moved to this is high pressure liquid. Okay, high pressure liquid. So this after reaching receiver, it has been completely converted into liquid. So at 3 minutes it is completely liquid. 3 minutes it is completely liquid. Here it is 3. So complete high pressure liquid is now passed through expansion valve or refrigerant control valve. So while passing through this expansion valve, what is happening? It is also known as throttle valve. Throttle valve. Throttle valve decreases the pressure. The function of the expansion valve or throttle valve or refrigerant control valve is it allows the liquid refrigerant under high pressure and temperature to pass at a controlled rate after reducing its temperature and pressure. Okay, so after it becomes a state 4. So 3 to 4, it reaches 4. What is happening? H equal to constant. It is getting expanded isenthalpically. So here isenthalpic expansion takes place. So the liquid becomes a low pressure liquid vapor mixture. Right? So here it is liquid vapor mixture. The pressure is low, temperature is also low. Low pressure, low temperature liquid is available at the inlet of evaporator. So why are you reducing its pressure and temperature? Because the answer is here in evaporator. So this is evaporator, right? So 4 to 1 evaporation takes place. 4 to 1 evaporation takes place. From in evaporator, what is happening? Heat is getting absorbed from temperature to be the temperature of heat is getting absorbed from or extracted from the space to be cool. From the space to be cool is if it is the temperature of that space to be cool. We have to maintain a T cold, a temperature called T cold. So it is the temperature at evaporator is TE. If heat should be if it should transfer from the space to be evaporated to evaporator, what should be the relation of T cold and TE? T cold should be greater than TE. So we have to lower the temperature. We have to reduce the temperature even lower than the T cold. So we have to get a temperature lower than the temperature of the space to be cool. Then only heat transfer takes place from that space to evaporator. So that is why we are applying an expansion valve. So by expansion valve means it reduces temperature and pressure also. So since pressure is reduced, naturally it gets sucked into the evaporator. The motion continues. The pressure difference makes the refrigerant to flow. The refrigerant will flow only if there is a pressure difference. Okay, so an evaporator consists of coils of pipe in which the liquid refrigerant at low pressure and low temperature is evaporated and changed into vapor refrigerant at low pressure and temperature. So here at 1 the state will be low pressure, low temperature, saturated vapor. So after absorbing you can see low pressure vapor, low pressure, low temperature vapor. So that is the working of, and the cycle continues. Okay, and it also again move to the compressor. Okay, so the cycle continues. So this is the working of the vapor compression refrigeration system. So here evaporation takes place, here condensation takes place, here compression, expansion, and in evaporator low pressure liquid vapor mixture get converts to low pressure vapor. Okay, in compressor low pressure vapor become high pressure vapor. In condenser high pressure vapor becomes high pressure liquid vapor mixture. In high pressure liquid vapor mixture then again get converted to high pressure liquid, and in expansion valve expansion high pressure liquid get converted into low pressure liquid vapor mixture again. So this process continues, so that what is happening actually, so that what is our function, this is the space to be cool, space to be cool, space to be cool, this is atmosphere or any other sink. So what is happening, what is the main objective of this refrigeration system? It is nothing but the heat should be absorbed from the space to be cool, or heat should be extracted. This heat is nothing but a refrigeration heat or refrigerating effect, QR, refrigerating effect. This refrigerating effect or this heat should be absorbed from the space to be cool, and that heat should be rejected to atmosphere, heat rejected. So heat should be continuously absorbed from the space to be cool, and heat should be continuously rejected to the atmosphere. So in order to continuously in order to continuously reject this heat and absorb this heat, we have to continuously run this cycle. So since the cycle runs repeatedly or continuously, continuous rejection of continuous absorption of heat from space to be cooled and continuous rejection of heat to the atmosphere takes place continuously. So that is the working of refrigeration system, vapor compression refrigeration system. So here you should note that in the conduit or in the path of the refrigerant, it continuously change from vapor, liquid, mixture, liquid, and phase change is continuously happening. That is why this system is called vapor compression refrigeration cycle, and that is the main difference of this cycle from that of Bell-Coleman cycle. There nothing like phase change is happening, only sensible heating or cooling is happening. So there no phase change is happening. There the air remains as gas itself. It does not get converted into its liquid form. Here the refrigerant is getting converted into liquid, and again converted into vapor form, that is evaporation and condensation. So here it is evaporation, here it is condensation. So these things are happening continuously. Yes. Thank you.